Charge is an immutable and indestructible property of matter. This means that it cannot be created nor destroyed, only transferred from one object to another. This is done by moving electrons from one surface to the next, leading to a deficit of electrons in one object, known as a positive charge, or an excess of electrons in another object, known as a negative charge. In this experiment, we sought to measure quantitatively and also qualitatively observe and describe the effects of charge over clear pieces of plastic tape, called Scotch tape. We did this first by laying a piece of tape along a countertop about 20 centimeters long and placing another 20-centimeter long piece of tape over top of it and ripping it off quickly. In theory, this would take the electrons from one of the pieces of tape and remove them from the other, leading to a negative charge and a positive charge in the respective pieces of tape. First, I moved my hand next to the piece of tape to see if it was attracted. My hand should be neutral, and charged matter is attracted to neutral matter, and it was attracted, so I confirmed our hypothesis that the tape was charged. Next, I took a clear plastic pen and rubbed it in my hair to generate a negative charge. This is a known fact that plastic in contact with hair generates negative charge. After charging the pen, I held it near the piece of tape. They attracted, indicating that the tape was likely a positive charge. Now knowing that this piece of tape was positively charged, I repeated the experiment to get another positively charged piece of tape. Next, I put a piece of tape over a gap between two books, loose but taut enough to where it maintained roughly its shape. And then I took the second piece of tape, also positively charged, and held it underneath. Recording the distance between these two using a camera and a ruler, I was able to determine the distance um, between these two pieces of tape when the second piece of tape, the upper one, began to stand up. It was approximately zero point 0.2 centimeters. The reason for measuring this specific distance was because I wanted to equate the force of gravity with the force of electric charge by finding the equilibrium point at which there was no momentum between the two, but they were still um, at rest. In doing so, I was able to equate the force, which is an easily found vector, using this equation here. Force is equal to mass times the gravitational constant of acceleration, 9.81 meters per second squared. And I equated that with the force due to charge, which is also known by Coulomb's law. Additionally, I equated the charge of the lower piece of tape with the upper piece of tape, an assumption I made because they were produced in a similar manner and because it made the experiment possible and much simpler to do. In doing so, I found this expression for the charge of each one of the pieces of tape. The distance between them at the point of equilibrium multiplied by the square root of the force due to gravity, found in this expression above, divided by the constant k. I put this in terms of microcoulombs to make the number more manageable by multiplying it times 10 to the 6. The force was found simply by equating it with the gravitational force, an easy task to do. In doing so, I was able to write this program, which takes inputs for distance, zero point 0.2 centimeters, and the length of tape, roughly 20 centimeters, and returns these values here. This one for the force due to charge, and this one for the charge itself of each one of the pieces of tape. Now, this charge is known to be positive, referencing earlier when we put next to a piece of plastic that was charged negatively, and they attracted. This was expected on both counts because we know A, that when it was next to my hand, that it was charged because charged matter is attracted to neutral matter. Additionally, we knew that the pen, which was going to be charged negatively, was either going to attract or repel. After knowing that it attracted, we knew that it was a positive charge on the tape. And of course, this experiment was very expected because the pieces of tape were charged in similar manners such that they would have the same sign charge, meaning they would repel each other. This was not unexpected at all. However, if we as humans decided to call electrons positively charged and protons negatively charged, would that affect the outcome of this experiment? Well, no, it wouldn't, because the repulsive force would be the same, since the charge of a proton and charge of an electron are defined to be the exact same, and their signs would ultimately cancel out, leading to both the same forces and the same charge, although they would be inverses of each other additively on the charge front, negative rather than positive. But that would make no real physical difference since the definition of charge is completely arbitrary and a matter of nomenclature entirely. Additionally, um, I was important to avoid contact with the tape as I was handling it because it is well known that matter will discharge into a large neutral object compared to its size, known as grounding. So if I was handling a piece of charged matter too much, it would eventually lose its charge from the charging process of tearing the tape and ground into me. I did not want that to happen. I wanted the maximum amount of charge possible between these two pieces of tape, especially since it was a humid day already, which decreases the attractional or the repellent force or attractional force between the two pieces of tape that are charged. This was my lab report, and I thank you so much for listening.